In this section, we will talk about a system of linear equations. A system of linear equations is a grouping of two or more linear equations where each equation contains one or more variables. In this section, we will talk about two equations and two variables. If you take a look at this example here, we have equation number 1 and equation number 2, and each equation contains two variables. A solution is an ordered pair to xy that satisfies both equations. Now, this is important to remember that the solution has to satisfy each equation of a system of equations. So if a point satisfies one equation but not the other, it cannot be a solution. A solution has to satisfy both equations. For example, determine whether negative 4 comma 16 is a solution to the system of equations. So in this case, our x value is negative 4 and our y value is 16. So we replace the y value with 16 and we replace the x value with negative 4. And we check, is that a true statement? So we get 16 on the left side, negative 2 times negative 4 is 8, and so we get 16 equals to 16. So this point satisfies the first equation. But for the point to be a solution, it has to satisfy not just one, but both equations. So let's plug this into the second equation. We have 2 times x, which is negative 4, plus y, which is 16. We want to determine, is that equal to 0? So we got negative 8 plus 16. We want to check, is that equal to 0? Now negative 8 plus 16 is 8. 8 does not equal to 0. Therefore, this point satisfies the first equation, but not the second, so this is not a solution. So in this section, we will talk about how do we determine the solution of these equations without just plugging in random points, hoping that one will work. So there are two different methods. The first method is called the substitution method. And we'll go over the steps as we look at the example. So example, solve the following system of equations using the substitution method. So step 1, solve one of the equations for one of the variables. And this here is important. In that first step, we must avoid fractions. Now let me show you an incorrect way of doing this. I have x plus 3y equals to 7. We're usually used to solving for y. So let's say I decide to solve for y, because the first step says solve one of the equations for one of the variables. So I take the first equation and I solve it for y as we usually do. So that means I subtract x from each side. And then this gives me 3y equals to negative x plus 7. Then since the y is being multiplied by 3, I divide everything by 3. And I end up with this. I end up with y equals to negative x over 3 plus 7/3. When I have fractions in step 1 of a substitution problem, that tells me I did not solve for the right variable. So if I see this kind of a case, that is incorrect. Okay, so which variable can we solve for that will not give us a fraction? And let's think about how the fraction came about. The fraction came about because we divided everything by 3 at the end. Until then, we had no fractions. So you always want to solve for the variable that has a coefficient of 1. In this case, x. All the other variables have coefficients that are not 1. So they're all going to give us fractions. So in step 1, we always solve for the variable that has a coefficient of 1. So we have x plus 3y equals to 7. We are going to solve for x, which means we are going to move the 3y to the right. And again, we solve for x because we want to avoid fractions. And the x has a coefficient of 1, which means we won't be doing any dividing at the end like we did with the 3. And so that'll give you x equals to 7 minus 3y. Okay, that's step number 1. Step 2. Step 2 says substitute the expression solved in step 1 into the other equation. So now we got x equals to 7 minus 3y. In step 2, we take this, so this is an equivalent expression, x equals to 7 minus 3y. In step 2, we take this and we plug that in to the other equation. So in the other equation, our other equation is negative 2x plus 5y equals to 19. but instead of x, I'm going to replace it with the 7 minus 3y. And the reason for that is that right now we can't solve this equation because we have different variables. We can't combine our like terms. But if I substitute the x with 7 minus 3y, then I'll have all y's. So I have the negative 2, which I'm going to keep the same, but instead of x, I'm going to replace that with the equivalent expression, which is 7 minus 3y plus 5y equals to 19. And that is step 2. Step 3, solve the equation found in step 2. So now in step 3, we're going to go through and we are going to solve this equation. So we have negative 2 times 7 minus 3y plus 5y equals to 19. When we solve equations, our first step is to clear fractions, which we don't have. Second step is to distribute. So we're going to distribute the negative 2. So we're going to get negative 2 times 7, that's negative 14. Negative 2 times negative 3y, that's a 6y, plus 5y equals to 19. Then I combine my like terms. So I have negative 14 plus 11y equals to 19. And then I add 14 to each side. So this gives me 11y equals to 33. And then I divide both sides by 11, and I end up with y equals to 3. A solution is not just a y value, it's an ordered pair, which means we have to solve for x as well. And we have three equations. We have x plus 3y equals 7, negative 2x plus 5y equals 19, x equals 7 minus 3y. It doesn't matter which equation we plug y into. We can plug y into any of the equations, and we will get the same answer for x. So to solve for x in step 4, I'm just going to use the first equation that says x, which is unknown, plus 7 plus 3 times y. So y is 3, so I have x plus 3 times 3. And all I'm doing is I'm replacing the y with the y value which I solved for, which is 3. And I'm going to say this equals to x plus 3 times y equals to 7. So that's x plus 9 equals to 7. If I subtract 9 from both sides, this gives me x equals to negative 2. And I always have to write my answer as an ordered pair. So my answer is going to be negative 2, comma, positive 3. And if I wanted to check my answer, I would take this point, negative 2, 3, plug that into both equations, and see if the left side equals to the right side. Okay, this next example we will do in class. The next method of solving a system of equations is using linear combination, which is also called elimination. So step 1, write each equation in standard form, ax plus by equals to c. So everything, all the variables have to be on one side, the constant has to be on the other side. Step 2, choose a variable to eliminate. Now you can choose any variable. Sometimes one variable's easier than the other, but it doesn't matter which variable to eliminate. So step 1 is done because in these both these equations, the x's and y's are on the left side, the constants are on the right side. So that's good. Step 2, we have to choose a variable to eliminate. So I'm going to, it doesn't matter, I can pick the x's, I can pick the y's, it really doesn't make a difference. I'm going to choose the x's. And whatever variable I choose, I'm going to underline that. So I'm going to choose to eliminate the x's. Now, here's how something eliminates. If I had like a negative 2 plus 2, that adds to 0, that eliminates. If I had like a negative 6 plus 6, that adds to 0, that eliminates. If I have a 5 minus 5, that adds to 0, that eliminates. But if I have a 7 and 5, that adds to 12. This does not eliminate. That does not eliminate. So we need to have this kind of a case. These are called additive inverses, which means we got the same number but different signs. We need to create additive inverses. So we need to make sure that 7 and 5 are they both turn into the same number, but one's negative and one's positive. So step 3 says multiply one or both equations by a constant in order to have the coefficients be additive inverses. So I chose the x's. The easiest way of doing this is that I'm going to multiply the first equation by 5 because the opposite coefficient is 5, and the second equation by 7 because the opposite coefficient is 7. And what that does is it creates the same number in each equation. Now that the x's are both going to be 35s. But I need to have one negative and one positive. So it doesn't matter which one I choose to be negative. I'm just going to choose the first one to be negative. I could have made the second one negative. As long as one is negative, one is positive. And then I'm going to distribute to both these equations. So I have negative 5 times 7x, that is a negative 35x. I have negative 5 times negative 3y, that's a positive 15y. And then I have negative 5 times 10, which is a negative 50. Then I have 7 times 5x, that's a positive 35x. 7 times negative 4y, that is a negative 28y. And then 7 times 9, that is a 63. What I did by using that is I created additive inverses, which means I got the same number, but I have opposite signs. So now the negative 35x and the positive 35x, these are now additive inverses, which means they're going to add to be 0. Now I can just go through and add these. So I have a negative 35 and a positive 35, that's 0. I got 15 minus 28y, that is a 13y. And then I have 50 minus negative 50 plus 63, which is a positive 13. And to solve for y, if I divide by y, or divide by 13 rather, then that yields y equals to 1. Okay, this yields y equals to 1. But I'm not quite done yet because I still have to find x. And now I have 4 equations. I got equation 1, 2, 3, 4. It doesn't matter which equation I pick. I'm just going to pick the first one. The first equation is 7x minus 3y equals to 10. But instead of y, I'm going to replace the y with the 1. So I have 7x minus 3 times y, which is 1, and that equals to 10. So I have 7x minus 3, that equals to 10. You know what? I apologize. I'm going to back up here. 15 minus 28 should be a negative 13. I'm so sorry. So this should be a negative 1. So I'm going to divide by negative 13. And I actually end up getting y equals to negative 1. I'm sorry. Something looked funny. So now that y equals to negative 1, I'm going to replace this y with a negative 1 to do it properly. So I'm replacing that with a negative 1. Okay, so now here's what we have. We have a negative 3 times a negative 1, which is a positive 3. So we got 7x plus 3 equals 10. I subtract 3 from both sides, so I get 7x equals to 3, to 7, and that means x equals to 1. I always write my answer as an ordered pair, so my answer is going to be 1 comma negative 1. My x value is 1, and my y value is negative 1. If I want to check my answer, I can take this and plug it into each equation to make sure the left side equals to the right side. Okay, we have another example, which we will do in class. Lastly, if a system of equations yields 0 equals to 0, then the system has infinite solutions. If the system of equations yields 0 equals to a, where a is any other number besides 0, then we get no solution. So for example, if I were to solve this using elimination, I choose a variable, so I'm going to choose the x's again. And I need to have additive inverses. So because I have a negative 2 here, I'm going to multiply the first equation by a positive 2. Notice that I did not multiply by negative 2. I only multiplied by positive 2 because I already have a positive and a negative. Okay, so you only multiply by negative if you want to change the sign, but the sign is already what we want. If the second x is negative, I want the first x to be positive. So I multiply by positive 2. This gives me 2x minus 2y equals to 8. And then I have a negative 2x plus 2y equals to negative 8. So 2x minus 2x is 0. This is 0. 8 minus 8 is 0. When I have 0 equals to 0, this tells me that I have infinite solutions. And that only happens when all the variables add to 0. If I had 0 equals to like 5, for example, that would be no solution.